So welcome to the AskTOM office hours for database and memory. My name is Andy Rivenes. I'm a database and memory product manager. We have a special guest, Mike Gleeson, with us, who's a member of the database and memory development team. So a real live developer that's going to help me co-host, help answer questions. So please remember that if you have questions, that's the main reason we're here. And you can just type them into the chat, and Mike will relay them to me, and so we'll hopefully get your questions answered. What we wanted to do today was focus on RAC and how RAC works or interacts with database and memory. And so with that, I think we can go ahead and get started. Oh, and everybody is muted and your video is turned off. So again, the only way we'll know that you have a question is if you type it in the chat. Oops. And then we'll give our safe harbor statement, which basically just says don't make any purchasing decisions on anything you see in this presentation. And I threw in a couple of slides just as a real quick review. This is actually our 5th AskTOM session for database and memory. So if you've been with us for any of the other previous series, hopefully you kind of know what database and memory is, but I'll give you, anybody who might not be familiar, I'll just give a real quick introduction. And database and memory is an option to Oracle Database. We brought it out with the 12.102 patch set. Obviously it's available in 12.2 and 18C as well. And the bottom line is database and memory is all about analytic processing. So analytic workload, it will accelerate using columnar formatted storage, and we have the ability to not only do analytics very fast, but since it's fully integrated in Oracle Database, as you'll see today, it's integrated with RAC and parallel query, and in addition to being focused on analytic queries. So fully integrated, and you don't have to make any application changes to take advantage of that. And that's kind of the intro to it. The real breakthrough with database and memory was the ability to have not only the traditional row store, but then have columnar formatted objects and being able to run analytics in that columnar format, which is much, much faster than the row store. If you want to go back and look at some of our previous sessions, you can see we did a demonstration to show the orders of magnitude difference that occur being able to access that data through the columnar format as opposed to the row format. We don't change any on-disk formats, so all of the other Oracle technology for the database works just fine. You don't have any restrictions, and we keep it simultaneously active and transactionally consistent, which means we basically preserve the Oracle transaction model so you never see data that's out of sync. If data has been changed, is not reflected yet in the Columnstore, you'll get it from the row store. But you'll always get a read-consistent view of the data, and so none of that changes with database and memory. Again, it's truly integrated into Oracle Database. And so that's kind of your quick introduction to database and memory, but let's move on to why we're here today. Let's talk a little bit about scale out, and that's really where RAC comes in, is scale out with database and memory. So in a single instance database, we'll have one column store. You allocate it with the in-memory underscore size parameter. It's allocated out of the SGA, and we call it the in-memory or IM column store. And it's limited by the amount of memory that you can allocate on the node, since we're talking single instance, the node that you're running on. So you can only have so much memory in a machine. You can only allocate so much of that memory to Oracle Database, and so then that obviously limits you on how large of an SGA you can create, and how much size you can allocate to the column store with the in-memory underscore size init.ora parameter. You can use serial or parallel queries with database and memory on a single instance node. Obviously, we've kind of talked about this, but we're only talking about CPU and memory access. So one of the ways to speed up access to or speed up analytic queries that are accessing the column store is to parallelize them. So parallel query works seamlessly just like it does in the row store. You can use either serial or parallel queries. And that becomes an important topic as we move on to talking a little bit about how database and memory works with RAC. So here I have a 4-node RAC cluster, And since we're limited on a single instance to the amount of memory that can be allocated to both Oracle database and the Columnstore, on a rack cluster, we now can scale out across that rack cluster. So we can now be limited only by the amount of memory that each node can, we can allocate to the Columnstore for each node, but across the entire cluster. And then you can obviously plug in more nodes if you need more Columnstore for your analytic workload. So I have a picture here of 4 Columnstores. You would set in-memory underscore size on each of the nodes, and then we'd allocate that amount of data to the Columnstore for each of the nodes. So this enables basically the ability to scale out beyond a single instance database. When we do this, it's essentially a shared nothing environment. One of the big takeaways with rack and database in memory is that IMCUs, we've talked a little bit about IMCUs, in-memory compression units. It's in our documentation, and we have actually a whole blog post that talks about an in-memory compression unit. But essentially, an object is populated in the Columnstore, occupies one or more IMCUs. That's essentially the, if you will, the extent for the memory allocation to each of the objects in the Columnstore. So unlike the buffer cache and cache fusion in rack, where we do ship blocks across the interconnect, we don't ship IMCUs across the interconnect. IMCUs are bigger. They basically are made up of one or more of 1 megabyte extents. And so it wasn't practical to try to ship all of the analytic data or the columnar formatted data across the interconnect to make it perform and to do the scanning. So what we did is we actually allocated it as a shared nothing environment. That requires using parallel query to access data on other nodes. So obviously you could access, if you're connected to say node 1 there, say node 1, you could certainly query the data that's in the Columnstore in that node, but to get to the data in nodes 2, 3, and 4, if I highlighted that, there we go. Whoop. There's some kind of like that. Hopefully you can kind of see that. If nodes 2, 3, and 4 have data, though, without parallel query, there's no way for us to access that data, again, because we're not shipping it across the interconnect and because it's a pure in-memory format. So that columnar formatted data is only available in the Columnstores that it's populated on. We'll talk a little bit about how we do that population in a few minutes, but this is a key aspect of rack with database and memory. So I want to make sure we talk about that, because then people will kind of normally ask the next question, well, what happens if one of the instances fails? So what do we do then? And so initially when an instance fails, obviously the instance is gone, but also the Columnstore data that's in that instance. Now, all of the data is always persistent in the row store because the Columnstore just reflects a pure in-memory columnar format of that data. But we won't be able to access that data. So in this case, a quarter or 25% of our data we can't access. So what happens? Well, the query will still run. Obviously, we'll have to have a parallel query to access the data in the other nodes. But we won't be able to access the data in the node that's failed. And so what will happen is we'll get that data from the row store. We'll pull it out of the buffer cache, or depending on the instance we're running on, or we'll go to disk to get that data. So obviously the performance of that query then won't be as good as if all 4 nodes were up and available. However, the application won't see an error. It'll just be, it'll just be a little slower. Now, there is the ability, if you have enough additional space on the other 3 nodes that are survivors, that survive the outage on the 4th node, that after a 5-minute timeout, that data can be repopulated into the other 3 nodes. Again, that just expects, or you have to have additional memory in these other 3 nodes to actually allow that population to occur. But assuming that you do have enough memory, that the data that was in the failed node will then be redistributed across the surviving nodes. And then obviously that data is in memory, and so now queries will be back to the speed, with the caveat that you won't have full CPU resources because one of your nodes is gone, but all that data will be available in the Columnstores that survive. And then if that node were to come back up, I guess I should have had an animation there. See if I I delete this, there we go. If that node comes back up, then we'll repopulate that data back to that node. And so that's the reason for the timeout, because if it's a short duration outage for some reason, there's no point in repopulating all the data that's in this node back over to the other 3 nodes. If this node's going to come back within a fairly short amount of time, we'll just repopulate back here. So that's kind of the story on distribution within a rack database and what happens if there's a failure. Because again, it is pure in memory. So that's kind of the database in memory part of the product. So let's move on and talk a little bit about the distribution and how we distribute the data across all these nodes, since we did say it's essentially shared nothing. So there's a default distribution. We support a distribution by row ID range, and I'll talk about what that means, by partition, and by subpartition. And then in 12.2, we have a new ability to distribute for service, which adds another layer to that. We're actually going to talk about in detail the for service distribution in our next AskTOM session, but I do have a slide where I'll discuss what that means. But in the deep dive details, we're going to talk about that in our next session, because there's actually quite a bit of information we can talk about with this this additional addition that was added in 12.2. So when you do an alter table sales or alter table in memory, the default is the distribute auto. So what Oracle will do is, based on the statistics of the segment or object, we'll determine, should we populate by partition, by subpartition, or by row ID range. However, it wouldn't be Oracle if we didn't give you choices. And so you can actually add a distribution choice right on the alter table command. And so you can say, well, I know that this data is skewed, so it's not going to be the same size because it's partitioned, and I want to do a row ID range even though the data is partitioned. And I'll talk a little bit about this idea of skew, especially when we get to the parallel query, but suffice it to say that since we're using parallel query to access this data, what our goal is to have a fairly even distribution of data across the column stores for each object. And the reason for that is so that we don't see parallel server processes finishing early on one or multiple nodes and taking a long time on another node because there was a lot more data, because then that gates your performance or your response time for that particular query. So the goal ultimately in distribution is to get an even distribution across the rack nodes, or across the column stores spread across the rack cluster. So I have a couple of diagrams here. We'll start with distribute by partition. I think it's conceptually fairly easy to understand. Where this really comes into play as far as distributing partitions across column stores is if you're doing hash partitioning. Again, the idea being that we're trying to distribute evenly across the multiple column stores. Our example, we're using 4 column stores. So here you see that we're going to distribute hash partitions. So we're going to get a fairly consistent size for each partition, and we're going to distribute those across all 4 nodes. Again, uniform partition or uniform access, because we are using parallel query. That's kind of the goal. And I'll talk a little bit later about this idea about in-memory partition-wise joins. And then we also, since we support partitioning by subpartition, that is also an option, both automatically, the auto, when you don't specify the distribute subclause, or if you're doing hash subpartitions, it makes sense to then distribute even subpartitions across the column store. Again, we're looking for even distribution of data for each of the objects across the available column stores in order to leverage parallel query and get the fastest response time possible. And then if you do have or don't have hash range partitioning, but if you do have a skew, if you will, then we distribute by row ID range. This is always the option for single tables, but this may also make sense for partitioned or sub-partitioned tables, again, in order to get that even distribution across all of the column stores. And at the level of row ID range, it will be distributed by IMCUs. We won't actually break up an IMCU, just for anybody on the technical side, because it would make sense to try to split an IMCU across the column stores. Again, non-partitioned tables is the default, but even partitioned or sub-partitioned tables may make more sense to do that because of the size differences. It may be that if you're using date ranges, that you may have busier months than others, and so you're really going to want to pick a row ID range, again, to get that even distribution. And then the distribute for service subclause. So this was added as part of the distribute subclause for both, mainly for active data guard environments. So this is how we support active data guard with database and memory, which was another 12.2 feature. The idea being that you can populate an object either on both the primary and standby. You can populate it on just the primary, or you could populate it just on the standby. And the way you determine that, or tell Oracle how to determine that population, is with the for service subclause. And so we're going to talk about that quite a bit in our in the next AskTOM session. So I'm not going to go into too much detail. The other benefit of the for service subclause, which we will also talk about, is the ability then to have support a subset of nodes. In other words, being able to populate an object on only maybe one or two of our, say, our 4 nodes. This becomes important. It's much easier to use this than it was in 12.1, where we were service dependent. And it makes sense for applications that require affinity to a specific node. Example we typically use is EBS. So EBS doesn't allow inter-instance parallelism. Parallelism has to be only on one node. So that means you need to be able to populate all of the data associated with your queries on a single node. And this helps you do that. Again, we'll talk about this in much more detail. The plan is we're going to try to whiteboard how all this works for you to make it a little bit easier to understand. But the bottom line is that this gives you even more flexibility at how you place objects across the rack cluster in 12.2 and above. And I won't go into too much detail about the services. We still use services, and the name section down below here, I'm actually not going to dive into because we're going to cover that all in our next session. But I did want to point out that it was an option and why you might make use of it. So, whoops, there we go. So parallel query. So I've mentioned that the in-memory column store is a shared nothing environment in rack. We have to use parallel query to access from a query running on one node to access the data on another node. So let's dive a little bit into how that works with parallel query. There are some caveats because we're just leveraging parallel query that's in Oracle database. So you have to still, you're still constrained by how parallel query works in doing this. So typically in our rack environment, our 4 nodes, again, we're going to populate IMCUs or parts of the data. Let's just assume single table where we're going to do row ID range. So parts of the data will be in each of the 4 nodes. So obviously, since if we're a user running a query connected to this node, then we have to use parallel query to access the other data in the column stores on the other nodes. Otherwise, we have to go to disk. And again, just reiterating that IMCUs are not shipped across the interconnect, and the reason was the size and the overhead of trying to not wanting to flood the interconnect with data. And so that's kind of the architecture. So that's takeaway number 1. So it's basically a repeat, but it's worth making sure that that you understand that. And then happy path, especially in, there's a slight caveat in 12.1 we see at the bottom, but so in 12.2, as long as the DOP of the query then is at least as great as the number of column stores the data is populated on, in this case 4, we see that we get at least 1 or more, that's what these little red dots are, 1 or more parallel query server processes, can't call them slaves, we call them server processes, across each of the rack nodes. The parallel query coordinator then assembles just the resulting rows from the access of the column store, or the objects in the column store on each of the other nodes, and assembles those and either returns them back to the evoking query or returns them into the higher levels of the execution plan. So really the only caveat is you have to have a DOP at least as great as the number of column stores, otherwise we wouldn't be able to access the data on each of the different column stores. So that brings up a conversation about how do we set the DOP. Again, this is a parallelism issue with Oracle database, and so we just have to honor how parallel query works. So there's two ways to do that. You can either set it manually, either at the segment level or at the statement level, or you can use auto DOP. And I'm going to flip to the next slide. Actually, I'm going to come back to that in a second. In 12.1, we required auto DOP. In other words, you had to use auto DOP to get to avoid this situation. In other words, we didn't know, we had a DOP of 4, we didn't know where the data was, and so we would just schedule maybe three parallel server processes on one node, one on another, and not schedule it on 2 of the other nodes, and so we'd obviously not be able to access all of that data from the column store. The reason for this is this slide. I guess I probably should have put it in different order, is that we keep track in rack of home location entries. In other words, we need to know where all of the IMCs or where all of the data lives on each of the different nodes across the rack cluster. So we have something called home location entries. We did a whole rack series, actually a 5-part series on rack on the blog, and we talk about this in some detail there as well. Bottom line is that in 12.1, the only way to access or make use of these home locations, if you will, was to enable auto DOP. In 12.2, so I notice I say in here in 12.2, whoops, 12.2 there, you don't need that. You only have to have a DOP at least as great as the number of column stores. Of course, the easy way to deal with that is to actually enable auto DOP there as well. But sometimes auto DOP doesn't perform the way customers would like. So we made the ability to set the DOP level available and still honor the location so that all of the data would still be accessed from the column store. One of the other caveats that I put down here is that with rack in database and memory, we do require some additional shared pool in order to basically have space to keep track of these home location entries. And as we said, and I have this note here for you if you want to go take a look at it. In addition to that, there's some additional space needed for locks on the database blocks. So our recommendation is to add an additional 10% of the size of the column store to the shared pool. Again, you don't have to remember all that. All you have to remember, and obviously the recording and the slides in the recording will be available to you. You can go look up this note on My Oracle Support, and we detail that requirement right in there, and we give you a formula that you can use to calculate that. So the only other caveat with database and memory on rack is that you do need some additional memory in the shared pool. So back to our story. So in 12.1, without auto DOP, we might not get parallel server processes allocated to all the column stores that we need. And with parallel query or auto DOP enabled in 12.1, we do. And then no matter which node we're connected to run the query on, we know that as long as our DOP, and if we've got 12.1 and auto DOP enabled, that we will definitely get a parallel server process on each of the nodes involved. That was a lot of talking. I've already used up about half our time. I did want to bring up one more issue with parallelism, parallel query, database, and memory. There's also another, and I guess I didn't put it in the slide. I should have. There is another caveat to parallelism, and that's a parameter called parallel min-time threshold. So parallel min-time threshold says that if a parallel query, and this has nothing actually to do with database memory per se, but if the optimizer determines that a query is going to run faster then your parallel min time threshold, the query will be run serially. And that was done so that we wouldn't unnecessarily run trivial queries with parallel query, because there is overhead in running parallel query and setting up the parallel server processes. With database and memory enabled, in memory underscore size is greater than 0, we've allocated our column store, we've populated objects into the column store. That parallel min time threshold, the default is 10 seconds. It gets set to 1 second with database and memory. Now, that's just something to keep in mind. However, if not all of your objects are populated in the column store, say you have your sales table is populated in the column store and you're joining it to another table and that table's not in the column store, then the parallel min time threshold would be set back to 10 seconds. So all of this I describe and I have a slide at the end so you can get the link to it. We have an implementation and usage white paper for database and memory. And all of this I describe in that white paper so that you don't have to remember this, other than maybe you ought to go take a look at that if you're running rack, so that you can make sure that you understand all the parallel query implications to doing that. And that's also in our best practices presentations that we're doing. And so we'll talk about that just to make people aware. Again, that's a parallel query feature or aspect to database and memory, because we are, again, leveraging all of the features of Oracle Database to run database and memory. And then lastly, I wanted to cover, because I have done a lot of talking and I'm sure there are some questions out there about Exadata. So there are some unique features that Exadata brings, or database and memory brings to Exadata, and I did want to briefly cover those as well. The first one is the ability, we talked a little bit earlier about the fact that if one of the instances goes down, somewhere in here, oh, that's right, that guy right there. Let's see if I undo the change I made. There we go. So if one of those instances goes down, then obviously the data that's in that column store is not available to the query because it's no longer in memory. However, in Exadata, we introduced the ability, so I can get, good. That's why I don't go full screen. I just, in presentation mode, I've been able to flip back and forth a little easier. We have the ability to duplicate or duplicate all. This is only an engineered system feature, but what it allows us to do then is to have IMCUs mirrored across column stores. So then if one column store were to go down, the other column store, the data that's in that column store would be mirrored across the other column stores. We'll talk a little bit about that in a second. That's especially, it comes back to dimension tables and the partial partition-wise join that I kind of mentioned earlier that I would talk about. The other big advantage of Exadata for database and memory is the ability to ship to move the rows return from parallel query to the query coordinator, and the ability to keep the duplicated IMCUs or duplicated data in sync more efficiently, because we can use direct-to-wire InfiniBand messaging. And so that is an advantage only available on engineered systems. And so the overhead of mirroring the data is much less than it would be on a non-engineered system. And so those are kind of two big advantages that Exadata brings, of course, with all of the other advantages that Exadata brings, especially now in 12.2, where we can actually populate objects in the flash cache in columnar format. And that's a topic for another day. But there's some definitely unique advantages to engineered systems. But what I wanted to cover real briefly was this ability to duplicate. So what this picture is supposed to show is that we now have mirrored IMCUs. So that IMCU and that IMCU are mirrored together. That IMCU, which I'm not getting and that IMCU are mirrored, and that IMCU and that IMCU are mirrored. So now if one of these nodes were to go down, the data is still available in one of the other surviving nodes, and so your SLAs are not affected because the query will still run in memory. And then I also wanted to briefly touch on another aspect of the duplicate option, and that's with dimension tables, typically in a warehouse with star schemas. It is entirely possible to populate, so the Ds are dimension tables, The F are fact tables, and this is a 3-node example, so you can actually see what's going on. And very often people will have a fact table that's partitioned, maybe a date range, partitioned across and then populated across multiple column stores. However, if you duplicate, or duplicate all in this case, the dimension tables, then for each join that has to occur between the dimension tables and the specific fact partition or fact table partition, that join can be done entirely within that. Let's see if I can highlight the node itself. Not going to let me. The node in question. And what that does is can improve the performance, because then we don't have to get rows from other column stores for the dimension tables, and the join can be performed entirely within the node we're interested in. And then obviously with parallelization, those joins can be happen in parallel. So that's partial partition-wise joins, which can be, again, significantly enhanced with the ability to duplicate the dimension tables across all of the nodes involved. So that's another feature of engineered systems and Exadata that can provide increased performance, especially if you're doing star queries in a warehouse environment. And with that, we've taken up actually over half the time. I was trying to get us back to having a little more time for questions. And so I'll throw it open. Do we have any questions that this might have generated, or other questions that you might have about database and memory?
Yeah, I am actually. There's a few.
Okay.
You touched on memory requirements. One question relates to that, and it was, could you elaborate on the shared pool requirements of memory mentioned in slides, sure, other than the different pools?
That was that slide there. So the shared pool requirements are basically, we need some additional memory for database block locks, because when we do the population or when we repopulate, we need to be able to serialize on that. And then we also need space for home location entries. So our best practice recommendation, that again is in our best practices in the implementation and usage white paper, and in this MOS note, is to take whatever your column store size is, take 10% of that, and add that 10% to additional memory to the shared pool, and then you'll be covered.
Okay.
So I don't know if it gets any simpler than that.
Yeah. So they just have to be aware to factor that in. So,
exactly.
Yeah. If there's nobody else itching, if anybody else has a question, please just mention it on the chat window. We can unmute you here, or I can relay your question. There was a question along, how do I tell if I accessed all of the data from the in-memory column store? Some people are concerned that they don't always know whether, even though their IMCUs were populated in, say, in a rack environment, how do they know that they really got the query, squeezed the maximum performance out of it, and actually touched on all that in-memory data?
Okay. So it's probably, so we'll use this picture as an example. So let's just assume, for whatever reason, that maybe we accessed in-memory data on 2 of the nodes, but we didn't on the other 2, or we want to know, how do we figure out whether that occurred? The simplest way to figure that out is with a SQL Monitor active report, because the SQL Monitor report will give you the information across all of the rack nodes as part of the execution plan in the activity. And what you'll see is in the, and I actually don't have an example, I should have set one up. And actually, if you go back to our, again, the implementation and usage white paper, I do have some examples in that paper showing SQL Monitor active reports. If you don't know how to use a SQL Monitor active report, if you go to our blog on the resources page, I have a technical brief where I describe how you can use it. It's very simple to make use of. But the bottom line is that the access of the object, the in-memory populated objects, will show in a SQL Monitor report either all of that data was accessed from the column store, or it'll show maybe some of it. In this case here, you would probably see half the data being accessed from the column store. The bar that goes across, well, I can't draw it. The bar that goes across for the activity will show half of it in memory CPU. We actually in the SQL Monitor Active Report, you can actually see the difference between normal CPU and in-memory access CPU. It's actually a different color, and you can hover over that. And again, I do describe that in the implementation usage white paper. And then the bar might be, in this case, half of it would be CPU or possibly I/O. And so that's I think the simplest way to figure that out. The other way is, if you don't want to make use of that, session statistics. So in the statistics, and we talk about this a lot, actually in our blog posts, we have some descriptions of the different statistics available. But in there, you can see that you'll have accessed some of the data from the in-memory column store, possibly some from session logical reads that access the buffer cache, and then possibly maybe physical reads or direct path reads. And so the other way to figure that out would be through statistics, because that's actually a runtime decision that will be made either because there weren't parallel server processes, or that part of the data wasn't populated in the column store, or for whatever other various reasons it can occur that we won't access all of the data from the in-memory column store. Again, the easiest way is SQL Monitor Action Reports, but session statistics are your friend as well, and we do have some examples of looking at those statistics in some of our blog posts.
Okay, thank you. Anybody else would like to chime in? If not, I have one or two here. One person wants to know, can they distribute by partition or subpartition without hash partition key? So how do they know how to distribute, basically, or what's our recommendation there?
So the answer is, of course, yes, because, whoops, I guess that's this one. Because wouldn't it work if we didn't give you choices? So you could certainly add to the altered table command, distribute by partition, this command right here actually, even if an override maybe the auto distribution, which might say row ID range. The risk you run, of course, is that then the data that's populated, so if those partitions then aren't evenly distributed, so there aren't a fairly close number of rows in each of the different partitions, when you run parallel query to access that data, you could wind up having one, say on this node, could run for much longer because it has to access much more data than, say, on the other three nodes. And so then the only risk that you run is your response time is then gated by the running of this query until this query returns the rows back to the query coordinator from the invoking SQL query. Your performance will be gated, or your response time will be gated to how long it takes to run on that one node. So that's the reason for making sure that if you are going to distribute by partition or subpartition, that data is uniformly distributed across the different column stores.
Okay, and kind of a related question, you touched on it earlier. You mentioned data guard. When the distribute for service, what are best practices in using that, and how does somebody know what they want to do there with and without data guard?
I remember where, there we go. So yeah, the distribute, the for service, this was added in 12.2. It supports, mainly was added for active data guard. So if the question is, when do I use active data guard with database and memory? The reason for using active data guard on a standby database would be for very often, since you have a primary standby or maybe one or more standbys, those standby nodes are typically not very utilized because they're ready for a disaster to fail over. And so very often customers will use a standby database for an active data guard database for reporting. And they'll run their reports and do most or a lot of their reporting on a standby database because it'll offload that workload from the primary. And so with database and memory in 12.1, we would create the column store, but we wouldn't allow you to populate it. In 12.2 now, you can populate objects in the column store on the standby database, and now that reporting workload could take advantage of database and memory as well as your row store, and perhaps provide significantly improved performance for your analytic reports being run on the standby database. So the question with forced service then is, how do I determine what objects would I populate on the standby versus the primary? And that's where the forced service subclause comes into play. As I said, you can choose when you do your alter table command to specify a forced service, and if the service is running on the primary database, that object will be populated there on the primary. If the service is running on the standby database, the object will be populated on the standby. Or if the service is running on both, or you haven't specified the forced service subclause, then the object will be populated on both instances, or both the primary and the standby database. And so that gives you complete flexibility to even have reporting objects in the standby, but not have to populate those reporting objects into the primary column store, because you don't really need them there. You only really need them on the standby. And then if a failover occurs, the objects will just follow the service. So depending on how your services are set up for failover, the objects will just follow those services. And so you won't have to do anything in addition to when you fail over your primary to your standby. Then your primary will still look the same. You won't be stuck with a bunch of objects that you don't want to have in the primary column store, because those are really just for reporting.
Right. So basically, when people have the standby, they're able to utilize the CPU for in-memory queries that they otherwise wouldn't be able to, without affecting the stand. Yeah. Okay.
Right. Exactly. So you can leverage all of your resources rather than having that just sit there, which is why people are using it for reporting.
Yeah. And we have another question that's related. It's a performance question. They want to know, do we have any performance comparison from using in-memory in rack, presumably, versus non-rack? I think they might mean.
No, I don't know of any performance comparisons between rack and non-rack. That's actually as much a generic Oracle row store database question as it is an in-memory question. Probably the best way to simulate that would be, obviously in your environment, because everybody's environment is different, would be to running parallel query against an environment that's a single instance database and then a rack database to verify that. I mean, the question of using rack is one of both scale out and availability. And then database and memory, again, one of the big reasons is the ability not only to have more data in your column store, but also then to leverage more CPU horsepower across the entire rack rather than being constrained to just a single node. I do not know of any like overhead comparisons or anything like that available that measures that difference.
Right, but as you say, it's sort of it's regardless of in memory or not, rack versus non-rack has its whole suite of scalability and whatever the app, you'd have to see what app you're running and basically, but in memory will benefit.
Yeah, well, definitely, because it's all still in memory query. Yes. Leveraging parallelism is, again, you kind of think about this, an object that's populated in the column stores in memory. So really all we have is for a workload footprint is CPU access to memory. And so one of the easy ways to speed up an in-memory query once it's already fully in memory running on a single CPU is to parallelize it so it can run on multiple CPUs. And so you just get that in Spades with rack, because now you can support that concurrently over a much larger user workload than you would be able to on a single instance database.
And related, there's another question here. It's how, with your using parallel query, how do you control the resource usage so that it doesn't overrun the system? That's a good question.
Yeah, sure. So in our example here, we have a 4-node rack. We're running a single user, no big deal. But what happens when you're running hundreds of users and they start lighting up? And they're using auto DOP, so the optimizer is trying to help, but it doesn't know what's going on right at the once it's parsed that query. And so then we have something we call Resource Manager. That's another feature available in Oracle Database. And Resource Manager fully supports database and memory. So the answer is to use Resource Manager, create a resource profile, and use Resource Manager to make sure that in-memory queries aren't dominating all of the CPU across your rack cluster or even your single instance database, so that you have enough CPU workload available for transaction processing or other workload that's not in-memory related.
Okay, and with that, there are no more questions on the chat line or the other questions I had here. So,
okay. I do want to point out that that we do have a significant amount of information available on both our in-memory blog. I always like to plug our database in-memory blog first, that we have a lot of articles. We actually have, again, I think I mentioned earlier, essentially a 5-part rack series on database in-memory and how it works with rack. We also have our in-memory white paper, technical white paper, and I did mention a couple of times the implementation usage white paper. Again, that's a great place to go to learn some of the issues with rack, the issues with database and memory, some of the things you need to know to implement we go through a methodology of implementation. I explain what workloads benefit from database and memory, along with some examples, SQL Monitor active report examples. And so there's a lot of good information there. We have a full in-memory in-memory white paper on in-memory aggregation, vector group by. We talked about that in, I think, the last session, the in-memory aggregation. There is the database in-memory advisor to help determine what object you should populate in the Columnstore. And then this AskTOM session, along with the other 4 AskTOM sessions, are all on the Oracle Developer Network. If you go back to our main page that you clicked on to join this session, we have listed there all of the previous sessions, and this one will be there as well. So you can go back and revisit the video. In addition to that, I've been adding portions of each of these videos that talk about the actual technical aspects of the focus that we've covered on our YouTube channel, along with a bunch of other videos. So we actually have quite a collection of videos on our YouTube channel as well. And so I just wanted to point out, and again, that my email address is right down there. If you have in-memory questions, I'm more than happy to answer them. I might even blog about those questions, since that lets other people know, broader audience to answer. If you've got a question, somebody else might have the same question. So we're really trying to get all of the information we can about database and memory out and available to you. And so I would suggest that the blog, I have all of these links on our resources page on the blog. Using the blog as a kind of your in-memory portal is a great way to start things. So I just wanted to make sure I pointed that out as other resources that are available to you. We'll call it a session. Well, thank you very much for attending. Our next session I will have posted. It's going to be the beginning. I think I did post it already. Beginning of August, we're going to go through in much more detail the active data guard and the subset of nodes that are possible with the for service subclause. And we're going to try to whiteboard that. I was thinking that would work for this, but I think this worked okay. But it gets a little complex when we start talking about a subset of nodes and then active data guard and how the different objects get populated between the two. So we're going to try to do something a little different, and we're going to try to whiteboard that session for you at the beginning of August. So with that, I think I'll thank Mike for being willing to moderate, and thank you very much for attending, and we'll call it a day.
Okay, thanks, Andy. Thank you all. Until the next time.